Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on March 2nd, 2026, just 2 days ago. It introduces a new architecture that builds mathematical symmetry directly into the model's structure, allowing it to solve complex Sudoku puzzles with nearly 94% accuracy while using only 2 million parameters. The paper is titled Symbol Equivariant Recurrent Reasoning Models, and as we'll see later, the way this model generalizes to unseen problem sizes is really impressive. And for those interested in the implementation, the authors have shared their code on GitHub. To understand the core innovation, Figure 1 compares the standard recurrent reasoning model on the left with the new symbol equivariant version on the right. In the standard approach, the puzzle is flattened into a two-dimensional matrix where specific numbers are baked directly into the features. By contrast, the new model on the right introduces a crucial third dimension for symbols, creating a 3D tensor. Inside the recurrent block, it applies attention first across positions and then across symbols, which guarantees that the logic remains consistent regardless of which specific numbers appear in the puzzle. Table 1 quantifies how this equivariant architecture translates into performance across different Sudoku grid sizes. On standard 9x9 grids, the symbol equivariant recurrent reasoning model achieves a fully solved rate of nearly 94%, significantly outperforming baselines like HRM and TRM. However, the real test is generalization. In the 4x4 mini Sudoku column, the baseline models fail completely with 0% solved rates. In contrast, the new model adapts perfectly, hitting over 95% accuracy. It even attempts larger 16x16 grids, which other models cannot even process due to fixed symbol vocabularies. Moving beyond Sudoku, Table 3 extends the evaluation to the ARC-AGI benchmarks and maze solving tasks. On the ARC-AGI1 dataset, shown in the first column, the symbol equivariant model achieves a competitive pass at T-score of 45.3, slightly edging out the tiny recursive model. The performance is also strong in the maze column on the far right. Here, the model reaches a fully solved rate of roughly 89%, which is a solid improvement over both the hierarchical and tiny recursive baselines. Table 2, meanwhile, examines test time scaling, which effectively asks whether giving the model more thinking time improves the results. The columns display the fully solved rate as the number of inference steps grows from 1 to 128. We see that while all models improve with more steps, the symbol equivariant model in the bottom row demonstrates superior scaling. It begins at 16% with a single step and climbs to nearly 99%, whereas the baseline models plateau much earlier, never breaking the 80% barrier. To understand exactly what symbol equivariance means, Figure A1 provides a clear visual definition. On the left, we see a standard input puzzle and the solution generated by the model. If we define a permutation that swaps the numbers 1 and 4, as shown on the right, the model's output changes in exactly the same way. The equation at the bottom formalizes this. Applying a permutation to the input is mathematically identical to permuting the output, which proves the model is reasoning about relationships rather than specific pixel values. Well, seeing that theoretical definition, Figure A3 now demonstrates how this translates into actual training efficiency. These three plots track validation performance across the ARC-AGI1, Sudoku, and maze tasks as the number of training samples increases. On the left, for ARC-AGI, the green line representing the symbol equivariant model climbs fastest, indicating superior sample efficiency. This advantage is even more dramatic in the middle Sudoku graph, where the green line shoots up to high accuracy almost immediately, leaving the orange and blue baselines far behind. This confirms that explicitly encoding symmetry doesn't just improve final performance, but drastically speeds up the learning process. Wrapping up, two takeaways stand out. Explicitly encoding symmetry allows models to generalize far better than brute force training, and doing so requires significantly fewer parameters. This suggests that the future of neural reasoning might rely as much on smart architectural choices as it does on raw scale. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.